Welcome to this session on the basics of geosteering, submodule 1 of 3. In this module, we'll introduce the fundamental principles of geosteering, explain the tools and methods used, and show how teams integrate drilling and geological data to keep wells precisely within their target zones. Let's begin with the objectives. In this submodule, our focus is to establish a clear understanding of geosteering, what it is, why it matters, and how it's applied. We'll begin with the definition, which frames geosteering as the active process of placing a wellbore within a geological target using real-time data and directional drilling. From there, we'll move into the components that make geosteering possible. This includes downhole measurement tools, drilling technology, software, and the people who interpret and act on the data. We'll then review the three main techniques. The first is the modeling, compare, and update cycle. This method integrates geological models with new drilling data. The second is real-time dip determination, which uses azimuthal imaging tools to understand layer orientation. The third is the distance to boundary method, a step change in technology that enables us to detect approaching reservoir boundaries remotely. Finally, we'll consider the people and process aspect that tie it all together from geoscientists to drilling engineers. This structure ensures we cover not only the technical tools, but also the workflow and teamwork essential for effective geosteering. Let's now define what makes a well truly successful. When we talk about success in well construction, we must consider both short-term and long-term outcomes. In the short term, a successful well is one drilled safely, without incidents such as blowouts, stuck pipe, or major non-productive time. It should be delivered on time, within budget, and it should encounter hydrocarbons at the expected rate, without producing unwanted fluids like water or gas. But drilling success is not only about short-term delivery. A well's real success is proven over time. In the long term, we measure success by sustained or extended production. A good well delays water breakthrough, reduces intervention requirements, and maximizes ultimate recovery from the reservoir. The graph at the bottom illustrates two wells. Well number 1 shows the short-term delivery focus, cost and time versus immediate return. Well number 2 reflects the long-term perspective, where production performance and recovery are the true markers of value. This distinction between short-term and long-term success leads us into the importance of accurate well placement in horizontal drilling. Here we see the practical interaction between drilling and geoscience when targeting horizontal wells. The top picture shows the plan. The 3 targets represent the reservoir zones we want to access. The plan is a smooth well trajectory connecting each of these zones. However, the reality is often different. Variability in the geology, measurement limitations, and drilling uncertainties causes the actual well path to deviate from the plan. This illustrates the importance of the interface between drilling and geoscience. For drilling engineers, the focus is on keeping the well on trajectory, optimizing rate of penetration, and maintaining safe operations. For geoscientists, the focus is on staying within the reservoir sweet spot. Successful geosteering requires balancing both perspectives in real time. Surveying is never exact. Every wellbore position has an associated uncertainty. The picture shows a horizontal well in green. The cumulative survey error at the heel of the well is plus or minus 40 feet of true vertical depth uncertainty. At the end of the lateral, the cumulative error has increased to plus or minus 84 feet of TVD uncertainty. The point is clear. As the well extends, the error in our calculated position grows. This matters because small positional errors can lead us to drill outside the reservoir. That is why understanding and managing uncertainty is central to geosteering. Looking at the zone of interest and the ellipse of uncertainty. The ellipse is a geometrical representation of where the bit could realistically be located considering survey errors. The longer and deeper the well, the larger this ellipse becomes. For geosteering, this means that while we are on target, the actual bit could be significantly above or below. Interpreting log responses and adjusting trajectory must account for this uncertainty. It highlights why real-time data integration and constant model updating are essential to accurate placement. Here we revisit the overview. We covered the definition, that is, geosteering is about geometrical placement. In simple words, it is drilling the line. That line is the intersection of the planned trajectory and the actual geological target. Let's move on to the next topic, which is components. These include drilling and logging technology, software platforms, and people. Each of these will be covered in subsequent slides. Geosteering relies on three categories of components. Downhole tools are the first. Drilling technology defines drillability, while drilling tools measure rock properties and geometry in real time. Motors and rotary steerable systems allow precise trajectory adjustments while drilling. Software and IT form the second category. Well placement visualization software enables real-time interpretation, and plan-ahead models allow forecasting of upcoming geology. Web-based data access ensures that subsurface specialists at remote locations can support the operation. People and process make up the third. Geosteering is a collaborative exercise. Coordinators manage data flow and decision-making. Client geoscientists contribute asset knowledge, while drillers bring expertise in technology and operational execution. In short, technology without people is incomplete, and people without data are limited. The true value of geosteering comes from integrating tools, software, and expertise into a seamless workflow. Let's now look more closely at the downhole tools themselves. Here are the fundamental downhole tools that make geosteering possible. First, direction and inclination measurements establish the well's position in space. These are transmitted in real time by the MWD system, often via mud pulse telemetry. Second, resistivity, density, and neutron measurements provide formation evaluation, telling us about rock properties. Third, the motor or rotary steerable assembly physically adjusts the well trajectory as needed. The picture shows the tools arranged along the bottom hole assembly. The power drive rotary steerable tool is behind the bit, allowing trajectory changes. Resistivity and density neutron sensors are placed further back, between 18 and 60 feet or more behind the bit, providing early indications of formation properties. The telescope MWD system, at 36 feet, transmits all this data to surface. The challenge here is that by the time the formation is being logged and surveyed, it has already been drilled. Therefore, to look ahead and be productive, we need a model and the ability to project ahead of the curve. Now that we understand downhole measurements, let's expand to the broader suite of logging while drilling tools. Logging while drilling LWD tools provide the data backbone for geosteering. The key measurements include gamma ray for lithology and azimuthal images, resistivity measurements to characterize fluids and boundaries, density and porosity for reservoir quality, sonic tools for acoustic properties, formation pressure tools, and distance to boundary measurements represent the latest step in geosteering capability. Each major service provider has similar offerings. Geosteering is a team activity. Clients, usually the operator's geoscientists, bring in-depth knowledge of the asset and the reservoir model. Their understanding of subsurface geology drives decision-making. Drillers contribute operational expertise, knowledge of drilling technology, steering assemblies, and the limitations of the rig. They are the ones who physically execute the steering instructions. Well placement coordinators act as the integrators. They understand LWD tool responses, software platforms, and well placement techniques. Their role is to balance inputs from geoscience and drilling, ensuring that the borehole is steered into the target zone. The key message is one team. Effective geosteering requires seamless communication and collaboration. When clients, drillers, and coordinators operate as silos, wells suffer. But when they function as a team, geosteering delivers optimal reservoir contact and long-term production value. Next, let's review the workflow that brings planning, drilling, and evaluation together. The geosteering workflow covers the entire well lifecycle. It begins with project planning, subsurface modelling and candidate well selection. This stage sets objectives and identifies suitable targets. Next comes pre-job planning. Here, the team defines the well objectives, selects technology, prepares the well plan and trajectory, and models the expected log responses. This ensures the team is prepared for real-time decisions. Then comes well construction. This involves applying drilling technology, optimizing the front end, monitoring operations in real time, and maintaining control over the trajectory. Completion and stimulation considerations are also addressed here. Finally, evaluation closes the loop. Formation evaluation is updated, reservoir models are refined, and production results are monitored. These lessons feed back into planning for the next well, ensuring continuous improvement. The key message is that geosteering is not a single action. It is a workflow that connects planning, drilling, evaluation, and learning. Now let's examine the three primary well placement methods in detail. There are three main methods for well placement. Method 1, model, compare, update. This is the conventional approach using non-azimuthal tools. The workflow is to start with a geological model, compare it against LWD measurements as drilling progresses, and update the trajectory to stay within target zones. It is iterative and relies on strong interpretation skills. Method 2, dip determination. This uses azimuthal imaging tools to calculate the dip angle of formations while drilling. By understanding the structural dip in real time, we can adjust trajectory with much higher confidence, particularly in layered or dipping reservoirs. Method 3, distance to boundary. This represents a step change. Using advanced remote detection tools like periscope, we can sense boundaries such as the top or base of a reservoir before physically drilling into them. This enables proactive steering, reducing the risk of exiting the zone. In practice, these methods are often combined, depending on reservoir complexity, tool availability, and objectives. In the next sub-module, we will focus on each of these methods. At the start of this sub-module, we set two key objectives: to define geosteering and to explain its basic principles. Let's reflect on how we've achieved them. We define geosteering as the process of steering a wellbore in real time to remain within the reservoir's most productive interval. We explored the components that make this possible: downhole tools, LWD sensors, software, and above all, teamwork and process integration. We explained the basic principles by working through the three well placement methods: model, compare, update, real-time dip determination, and distance to boundary. Each method represents a different level of capability, from conventional log interpretation to advanced remote sensing of reservoir boundaries. Along the way, we highlighted how success is defined, both in the short term through safe and efficient drilling, and in the long term through sustainable production and recovery. We also examined uncertainty and how it impacts placement. That concludes Submodule 1 on the basics of geosteering. Please proceed to the quiz to test your understanding of the material we've covered. Thank you for your time and attention, and I look forward to continuing with you in the next submodule.